All right, thank you. Thanks for inviting me. So this is joint work in three parts with Fares Hedayati, who was a PhD student here, is now at ODESK, partly with Wouter Koelen and Alan Malik, who are in the front row over here. And the third part is with Wouter and Alan and A.G. Takimoto and Manfred Wormuth. All right, so I'm talking here about prediction games where we play a repeated game with an adversary and we're aiming to predict something in the case of a discrete set of outcomes. At each round, we make some prediction from, so we call that AT, that's our action at time t from an action set A. The adversary chooses some outcome, YT, from a set Y, and we, the player, incur a loss that depends on our action and the actual outcome. So we could think about the Breyer loss, which is this squared Euclidean distance between our prediction and the outcome, for instance, if we're in a vector space. And that's one of the losses that we'll consider. Okay, and we keep on going in this way, round after round. And the aim is that at the end of it all, we have a small regret. So the sum of the losses that we've incurred along the way is not too much bigger than the best we could have done in retrospect for that particular sequence of outcomes. Okay, and we may do something a little more complicated where rather than thinking about the infimum over the set of actions we had to choose from, we have some different comparison class, potentially smaller comparison class that we're competing with. Okay, so they're the kinds of problems that I'm going to consider here. These universal prediction problems, completely deterministic, they're making very weak assumptions on the process generating the data. So that's one of the really appealing things about understanding prediction games, so game theoretic formulations of prediction problems. And it means that if you are in a probabilistic setting, then you can use effective methods for these problems to successfully solve probabilistic problems. So you're kind of getting at the deterministic heart of a decision problem, and in many cases, they're closely related to standard statistical methods, and you can view the positive results in this setting as strong robustness properties of those methods. But in this talk, I want to talk about specifically the case where we can actually efficiently compute optimal strategies. So we're playing the best possible at every step along the way. So, that's something that, of course, such a thing exists, but the cases that I want to talk about are cases where they're things that can be efficiently computed. Okay, so just to add a bit more detail to that, so the regret is the quantity of interest, right? It's the sum of our losses versus the best we could have done in retrospect. And we're interested in playing, the player does the best it can, the adversary has best response, and so on all the way through for T rounds of this game. And that alternating inf-sup sequence of this regret is the value of the game. And the game's specified by the loss function, the outcome space Y, and our action space A. And a strategy is a mapping from what we've seen already, the sequence of outcomes, to our choice of the actions. And so we can think of this inf-sup, the inf there, we could think of as just, for a given strategy, we've seen this sequence of outcomes y1 through t minus 1, and then we make some choice of what's the right action to play. And so a minimax optimal strategy is the mapping that actually achieves the value of the game. Minimizes over strategies, the maximum over those sequences of outcomes. Okay, so we want to know, what's the minimax regret, what's an optimal player's strategy, an optimal adversary strategy, when are these things efficiently computable in particular, and how do they depend on the various characteristics of the game, on the loss function, and we'll look at several cases, I'll tell you about these in a moment, and the various parameters that specify the game, the outcome space and the action space. All right, so this is the outline of the talk. I want to look at how we can compute these minimax optimal strategies. It's just a simple dynamic programming sort of formulation of it, conceptually very simple, but we're interested in cases where we can actually efficiently compute those solutions. The first part is all about log loss, so closely related to the last few couple of talks, closely related to this universal compression idea. The second part is about Euclidean loss, and I'll probably skip over some of the details of that. And the third part is looking at a fixed design linear regression game. Okay, so minimax optimal strategies. That's the value of the game we saw a moment ago. And we can easily write a recursion for that, right? Once we've seen all t outcomes, then that specifies the second term there in the regret, the best we could have done. And then we can just iterate backwards doing this min of our choice, max of the adversary's choice of loss plus the value to go one step further, right? So we iterate that backwards, and that gives us, when we have seen no outcomes, that gives us the value of the game. Okay, so what we're interested in is that recursion, and in particular, what's the minimizing action for any particular sequence of past outcomes, so for any history. So to play the minimax strategy, we just need to compute that value function and then find the minimizing action, the one that, given the adversary's best response, minimizes this loss plus value to go. Of course, that's hard because there are many different histories that we might be faced with, right? So this value function is typically a very complicated beast. Whoops. And so the question is, when can we efficiently compute the value function? And typically it's a function of some compact summary of the history that we've seen so far. I'm saying typically in the cases where we can efficiently compute it, I guess. Okay, so I'll probably skip over this. So there's a small set of prediction games. Let me zip past this. There we go. Small set of prediction games where we can efficiently compute the optimal strategy. What I'm going to talk about in this talk is the case related to universal compression, log loss, and some results we have there for cases that where simpler strategies are optimal. The quadratic loss, so the game that the nice cartoon at the start illustrated. That was Wouter's artwork, by the way. And the linear regression case. So this adversarial formulation of fixed design linear regression. Okay, so that's the agenda. I want to start with log loss. So here you can think of this as a sequential probability estimation problem, where we're looking at the sequential adversarial form of, or deterministic form of, minimizing KL divergence, right? So we make a prediction that's a probability distribution, or I guess a density, strictly speaking, a density with respect to some measure. Okay, the cases we saw in the previous two talks were with respect to the counting measure. And we pay a cost that's the negative log of our predicted density of the outcome that we see. The regret, of course, is just this difference of the log probabilities so difference of two likelihoods, a maximum likelihood and a log likelihoods. A maximum log likelihood and sequence of predicted densities. Okay, so first observation: these strategies are always can always be viewed as joint densities, right? So given a history, the previous sequence of outcomes y1 through yt, if we have a mapping from those histories to densities on y, well then we can just multiply those up to give us a joint density, right? So every strategy is just a joint distribution on outcomes, and then the regret is just a log likelihood ratio, right? It's the maximum log likelihood versus log of our predicted joint density. Okay, so these sorts of problems have a big history. You can view them as sequential probability prediction. They're equivalent to this notion of sequential universal data compression, or there are very closely related repeated gambling or investment problems that are the same. Long history in several different communities. Okay, and the optimal strategy is known. It's normalized maximum likelihood. It's been known since the 80s. So what you do is every strategy is a joint distribution. The optimal strategy for a game of length t is assigns a joint probability to a sequence of outcomes that is proportional to the maximum likelihood. Okay, so you just look at for any sequence y1 through yt, you can compute the maximum likelihood, and then you're going to have some normalizing factor, and that gives you the joint distribution. And Shtakov showed this was optimal a long time ago. Very simple proof that involves showing that every sequence has equal regret for this strategy, and so anything that doesn't equalize regret necessarily has some sequence for which its regret is larger. And so how would you actually use this? This is a joint distribution that's specified, so you have to go and compute conditional distributions. So we've seen some history y1 through yt minus 1, and we want to compute the conditional distribution of yt given that past, so we're integrating out the things beyond t or beyond t minus 1, and that's the computation we have to do, and that's a big integral, and the question that I want to look at in this part of the talk is, when can you do something that's computationally cheaper but still optimal? I guess maybe that's the wrong way of saying it. When is computing these integrals actually the wrong way to compute the optimal strategy? Because normalized maximum likelihood is the unique optimal strategy. And the two cases that I want to look at are versions of NML where we act as if we're at the last step, and so the integration that we need to do here is just over a single future outcome, so it's a simpler thing. And the other case is a Bayesian strategy. And so the first of these is sequential NML. All right, so this is where we pretend that this is the last prediction. So it's just, we've seen t minus 1 things, and we act as if our next step is the very last one, and we do the optimal thing as if that was what would be the optimal thing if that were the case, which is NML. So the conditional calculation then is just this integration over a single outcome. And that's known to have an asymptotically optimal regret, but what I'm interested in here is when is it actually optimal. So the punchline is that it's optimal precisely when this sequential normalized maximum likelihood viewed as a stochastic process is exchangeable, right? Which means you can switch around the order of the indices, and you get exactly the same density. So exchangeability of this stochastic process is equivalent to that being the optimal prediction strategy. That means you can ignore the horizon, right? Act as if you're about to finish the game after the next step. And I'll skip over the proof there. It involves this equalizer property for NML. Pretty straightforward. So the other class of strategies that I wanted to say something about is Bayesian strategies. We have some prior distribution pi on our model, and the Bayesian strategy assigns a joint distribution that's just the expectation under that prior of the density. And of course, we have the nice Bayesian machinery, right? We can sequentially update our prior given one more piece of information. We just multiply whatever the prior has become, the previous prior by the likelihood to get the posterior. So that's again a simple update. I want to highlight so Jeffreys prior is going to feature here. The Jeffreys prior is the one that's proportional to the square root of the determinant of the Fisher information. And that's something that has been widely studied. It has attractive properties, including the fact that you can change the parameterization and it doesn't change the distribution. So this is something that just pops up. It turns out, we'll see in a moment, this is the right prior. And there are various asymptotic optimality results for prediction with Jeffreys prior. Okay, so here's the main theorem, and I'm sweeping some conditions under the rug here, but in the case where the maximum likelihood estimator has an asymptotic normality property, then you have equivalence of all of the following statements. So the first two we saw earlier, right, that ignoring the horizon leaves you with an optimal strategy precisely when this sequential NML is an exchangeable stochastic process. But turns out that means that you're in a situation where you could also compute the normalized maximum likelihood, the optimal strategy, using a Bayesian strategy, right? And they're equivalent. Any Bayesian strategy, turns out has to be a Bayesian strategy with Jeffreys prior. And the same thing can be said for sequential NML. So, Jeffreys prior is it. This is telling us that if we can ignore the time horizon and still be optimal, then we should. That's the same as doing a Bayesian prediction with Jeffreys prior, and Jeffreys prior is essential here. And Jeffreys prior really arises. I mean, in 2 words, it arises because the asymptotics pop out because we've got this property of exchangeability means we can go off to infinity, and the asymptotic normality is what makes Jeffreys prior the right thing in this setting. Okay, so I'll skip over. So we can characterize one-dimensional exponential families that have this property. Oh, and by the way, they exclude the Bernoulli case, right, that we've seen before. Jeffreys prior in the Bernoulli case won't do. Okay, so the second part of the talk is on Euclidean loss. So this is a game where we're working in a vector space, and the loss is the squared Euclidean distance between our prediction and the outcome, times a constant factor, and the adversary is constrained to some set in RD. The regret is the same old thing, and I guess I'm pretty much going to just state the main result. So this blue-green shape is our outcome space. This is the set that the adversary is restricted to. It's hard to see here. This is the center of the smallest ball that contains that set, and it has a certain radius. And the point is, the main result is that for any closed bounded set, the Minimax strategy depends only on the center of that smallest ball. The optimal regret depends only on its radius. And the optimal strategy in this case is given a sequence of n outcomes. So far, you take the sample average of those and take a mixture of that with the center. So you're shrinking towards the center at a very precisely, a prescribed rate. You shrink towards the center, and that's your prediction. And the optimal regret depends on the radius of this smallest ball and on these coefficients, the alphas. And there's a specific form for the alphas. So this is always a number less than 1, and looks rather like 1 over n, and that gives a regret that looks rather like log t. Okay, and I'm going to skip. So there's the specific form for the coefficients alpha. So I'm going to skip over some of these details. Similar sorts of ideas pop up in the linear regression case, which I want to get to. So let's jump past that. And just say, the high-level idea of the proof is that, we can always find a simplex of contact points that kind of constrain this smallest ball, right, and stop it from getting any smaller in some sense. So that's a subset of our set Y. For that subset, the regret is this big, and so the regret for our original set is at least that big, since this is a subset of the adversary's constraint set. And we can look from the other side at this smallest ball. That's a superset, and it has exactly the same regret. So that's a big picture idea of the quadratic case. Okay, so, and this thing grows like log t, and you can get the second order terms, and if you look at things, it's like a constant factor that we're buying here. This looks like a constant factor. This is the simplex case. Okay, so let me get on to the online linear regression problem. So here, this is a square loss again, but it's a regression setting. So we have this side information, right? So we're talking. The protocol is, we've got the length of the game is fixed in advance. The set of covariate vectors is fixed in advance. So it's a fixed design linear regression problem, and there's some constraint set, constraining what the adversary can provide to us as the labels, the real valued labels. And the protocol is, for each round of the game, we make a prediction of what the the value yt will be, and the adversary reveals it, and has to satisfy these constraints, right? That the sequence y1 through yt satisfies some constraint. I'll say a little about different constraints in a moment. And then we incur a loss that's just the squared difference between our prediction and the actual outcome. Okay, so it's a sequential fixed design linear regression sort of a game, and the comparison class here is, we're allowed to predict any real number, but we're competing with the best linear prediction, right? So this is a least squares comparison. Okay, so what would we do if we were in a probabilistic setting where we see, for instance, a fixed design and the y's come from a linear model with uncorrelated errors, mean zero uncorrelated errors? We do ordinary least squares, right? So given this sequence of xy pairs, we'd estimate the parameter by taking our design matrix X, take X transpose X to the -1 times X transpose Y, right? That's our estimate for the parameter vector. And we plug that in for each X to be our prediction. And so in an online or a sequential setting, we might do something of this flavor, right? We'd take maybe the X transpose X for the points that we've seen already, and the corresponding X transpose Y, and use that for our estimate. Maybe we would regularize this in some way. So I just wanted to pop those up as a reminder of what ordinary least squares look like. So this is ridge regression. If we added some regularization term, then we'd be shrinking our parameters in different directions. So it turns out, subject to some constraints, right? So the adversary has these values yt constrained to have absolute values smaller than some bound. The optimal strategy, turns out, uses some simple sufficient statistics. Let's consider this sum of yt times xt. And the Minimax strategy is linear. So it's very much the flavor of least squares. It's this, to predict yn plus 1, we use xn plus 1 transpose times some matrix cn plus 1 times this analog of x transpose y so far, where the c's are, we take into account the xt transposes so far, and we also take into account the future ones with a very precisely prescribed weighting, right, using these. So this is a recursive definition of the CTs. And you can compute the maxi-min distribution as well, has the same expectation. You can compute the value to go, and it's quadratic in this state. Also includes a second order term involving the sum of the squares. Okay, and there's a little fine print here, right? So these bounds that we have, we can't too tightly constrain our adversary, right? Otherwise, making a linear prediction like this, if the adversary is too tightly constrained, then we should be making some clipped prediction, and then our value to go becomes a very complex function. And so these are the cases satisfying these conditions are the cases where we can come up with an easy to compute value to go. Okay, so they're a little strange, those conditions. I'll say two words about those in a moment, but so we're in the box constraint case. One thing I wanted to point out, so we get that the regret looks like this quantity in terms of these x transpose cx values, and they're what arise in here, right? So if we think about this as being an analog of ridge regression, where we have some shrinkage that's in every direction, what we're adding in here is shrinkage that's in a direction that's hedging against future values of these future directions, and the amount of shrinkage depends on the contribution to regret that we're going to see from these future x's. Okay, so the term that, each of these terms, I'm sorry? So you can think of that as the optimal shrinkage that arises analogous to the.
Not depend on B. Is this a constraint on nature, or?
B is a constraint on nature. The algorithm doesn't need to know B, right? So actually, and if you think about it, this is saying that the yt in absolute value is smaller than bt. and there's a condition that says, those constraints can't be too tight on the adversary. But actually, the adversary should be pushing yt out to maintain this constraint. So the natural thing to consider is what happens if you impose an ellipsoid kind of constraint of exactly that sort, right? So think about constraining the adversary in this way where the sequence is constrained so that sum satisfies an inequality of this kind. And it turns out, the optimal strategy there is the same thing, and the minimax regret is exactly this upper bound. Right? It has even a stronger property that we have an equalizer property, that the regret of this strategy for every sequence is equal to the sum of the y squared x transpose cx. So in particular, if you're on the surface of the ellipsoid, every sequence has exactly that regret, which is kind of striking and analogous to what happens in the log loss case, this normalized maximum likelihood case. All right, so the strategy doesn't need to know the constraints. There are several open problems. The most obvious one is how can we move away from the fixed design setting, right? So, what happens if we know we're in an analog of a transduction setting, right? So we know the x1 through xt, but we don't know what order it's going to be presented in. And we'd like to understand how to do things outside the fixed design setting as well. All right, thank you.
Time for one or two questions.
Concerning the log loss, you said that there are some conditions where you have asymptotic normality of the maximum likelihood, so regular, some kind of regular. Does it go as far as
right. I mean, so you could define, you could come up with sufficient conditions for that. I mean, all we really need is that we get asymptotic normality, right? So it could be that under these weak conditions that imply, the weak sort of regularity conditions are classical things.
If I remember, well, the first thing that looked like that was the analysis of and just on the
I'm sorry?
Oh, yeah, what's the name of the slide? Minimax or maximity difference prior in.
Right.
Bernstein von Mises theorem and the homemade Bernstein von Mises theorem. Do you use that kind of thing too?
No. So they were interested specifically in getting these, optimality in cases where the specific strategies we consider are not optimal. You don't have the Bayesian with Jeffreys prior being optimal. And so they're looking at how you can make these small changes near the edge of the simplex. I mean, very much like the last talk. So different kind of issue. We're looking at where we can actually compute the